Hello dear students, welcome to the lecture series on microelectronics. This is lecture number 28. Dear students, today we will see the high frequency response and its general considerations. Now whenever we talk of high frequency response, or basically the frequency response of any amplifier, then a lot of considerations that we need to be undertake. Now specifically when we deal with respect to high frequency response of any amplifier configuration, I need to be dealing with a lot of capacitances, specifically the parasitic capacitance. Now when I say high frequency response, what are the capacitance that will impact the amplifier configuration? We will going to have a thorough discussion in this today's lecture. Now before heading further, now we saw in the last class how we can use the common source and common gate amplifier with active load as one of the load, and we had a thorough discussion on how the input and output resistance and the overall gain of those amplifier configuration behaves when we replace the discrete or when we replace the resistive load with an active load. And in today's lecture we are going to move further. We are going to talk of the, as I discussed earlier, I am going to talk with respect to the high frequency response of the MOS amplifier configuration. Once students understand this particular concept, he will be in a position to understand what will be the key elements that are required in order to obtain the high frequency response for any amplifier configurations. Before moving further, let's try to figure out which level of learning this today's lecture fall in. Like I told in the previous lecture, Bloom's taxonomy is a set of 3 hierarchical models that are used to classify the educational learning objectives into different levels of complexity and specificity. Now there are 6 levels under Bloom's taxonomy: level 1, level 2, level 3, level 4, level 5, level 6, and today's lecture fall under the category of understanding the concept, hence I name it as level 2. Now in the lecture number 16, we had a thorough discussion, or we have a broader picture on the frequency response of an amplifier, and we plotted the 3dB graph of the midband gain graph of the amplifier configuration, and we figured out how do I obtain the low frequency response and how do I obtain the high frequency response, or basically we figured which are the capacitances that fall or that definitely affect the frequency response in terms of its lower band frequencies and in terms of higher band frequencies. And we are specifically more interested in the midband where the gain is remained, or where the gain is retained constant. We are not worried about the lower band frequency. We are much worried about the midband and the higher band frequencies FH, because FH typically defines up to what maximum frequency a particular amplifier can be operated without having a 3 dB roll-off in its midband gain. So that's very interesting and that's very important whenever we talk of an amplifier, because we don't want our amplifier to get limited itself to very minimal frequency. We want any amplifier to work at the highest frequency without having any drop in the gain. And in order to ensure that our amplifier works at a certain midband level or at a constant gain, I need to be specifically understanding what is its higher cutoff frequency or what is its upper cutoff frequency FH. Now if I know how to what is its FH, then I can say up to this particular frequency my amplifier will be acting as a constant gain amplifier without having any deviation in its gain or without having any distortion or roll off in its gain. Hence FH becomes very important to figure out the response of any particular amplifier configuration. Now if I want to decide this is the amplifier which works at this particular frequency, at higher cutoff frequency, then I should be knowing what is its FH. In order to know what is its FH, I need to determine the high frequency or the upper cutoff frequency of a particular amplifier configuration. So in order to figure out FH, there are multiple techniques to figure out the FH we are going to in briefly discuss about those particular techniques. Now basically the amplifier circuit are mainly intended to fabricate using IC technologies, and they do not employ the bypass and coupling capacitors. And there are various stages in an IC cascade amplifiers and are directly coupled or DC amplifiers. And the third or the main important point which I discussed just now is gain falls off at certain high frequency, but no reduction at low frequency. This high frequency roll off, whatever we speak very oftenly, is mainly because of the presence of internal capacitance of the transistors. So that we are going to figure out on what all factors the high frequency or the gain rolls off at the certain high frequency. Now this is the graph that I was talking. I'm just taking the high frequency response. So FH becomes very important for any amplifier configuration to ensure what is the maximum frequency up to which the gain will remain constant, and or the gain will be retained at the maximum level without impacting the operation of the amplifier. The amplifier gain with internal transistor capacitances can be written as AM multiplied by FH of S. Now this FH of S is nothing but the upper cutoff frequency, and this is the midband gain. Sometimes it is also called as low frequency or DC gain of the IC amplifier. Now gain is usually expressed as a function of complex frequency variable S in its general form as represented over here. And the gain AM can be determined by analyzing the amplifier equivalent circuit and neglecting the transistor internal capacitance. This is what we have been repeatedly doing in all the previous lectures, right from the very beginning of the lectures, where we analyzed where we did the gain or where we figured out the gain of the amplifier, discrete MOS amplifiers, whether it could be common source, common drain, common gate, and in the previous lecture itself we figured out the gain of the common gate amplifier using active loads. So we have been constantly doing all these sort of exercises in order to find the AM. So then that's not a big issue. I can use any technique either by using its T equivalent circuit or either by using its small equivalent circuit. I could be finding the AM. But the point is, how do I determine the FH? Now, according to the transistor internal capacitance, the gain acquires the factor FH of S, definitely. So when I talk of transistor's internal capacitance, then FH of S will come into picture. Now, when I consider FH of S, then the term known as transfer function will come into picture, where I express my upper cutoff frequency transfer function in terms of its poles and zeros. Now this is what the expression I usually represent for my FH of S, and as S tends to 0, FH of S tends to 1 and the gain tends to 0. So as simple as that. So I need to be considering these particular cases. Therefore the general form of the transfer function of the amplifier can be rewritten in this format. A of S is equal to AM, FH of S is equal to AM multiplied by 1 plus S by omega Z, so and so, divided by 1 plus S by omega P1, where omega P1 stands for the real poles and omega Z1 stands for the real transmission zeros, that is poles and zeros of the transfer function. Moving ahead, how do I determine the 3 dB frequency? That is, usually FH is typically known as 3 dB frequency, because that is the frequency where the gain rolls off by 3 dB. Usually we try to estimate FH in terms of omega, where we try to represent FH is equal to omega upon 2 pi, and in terms of its zeros and poles, we say that zeros at infinity or at high frequency has little significance in determining the omega H, whereas the poles play a vital role in determining the high frequency response or the FH of an amplifier configuration. Typically, if any one pole, say omega P1, is at low frequency than any other poles and zeros, then that particular pole, omega P1, has the greatest effect on the amplifier frequency, that is omega H, and omega P1 dominate high frequency response of the amplifier, and the amplifier is said to have a dominant pole response. So under this particular condition, the poles will play a vital role in determining the higher cutoff frequency. So to summarize in one sentence, if omega p1, that if the dominant pole is having a more impact than any other poles and zeros of the entire system, then fh of s can be written as 1 upon 1 plus s by omega p1, which simply represents the transfer function of a first order single time constant low pass network. Because mainly the intention is it is very insimilar to the simple low pass network transfer function, whatever we are going to discuss with respect to amplifiers upper cutoff frequency. Now if dominant pole exists, omega h determination is very simplified. I can say that particular frequency where the dominant pole is existing, I can consider straight away that is the frequency where that pole is existing will be the frequency of the, or will be the highest frequency of my amplifier configuration. Now this typical situation is encountered especially in the common source amplifier with respect to MOSFET or common emitter amplifier configuration with respect to BJTs. We'll try to see that particular implication of omega h in terms of common source amplifier in the subsequent lecture. Now what is the main rule of thumb? The rule of thumb is dominant pole approximation. We need to be figuring out that one particular pole which is very dominant in the entire network, and that dominant pole can itself be used as a pole which is represented or which can be taken up as FH. So in terms of the Bode plot analogies, or in terms of control system analogies, I can say dominant pole exists if lowest frequency pole is at least 2 octaves, a factor of 4 away from the nearest pole or 0. Then if dominant pole does not exist, then we use an appropriate formula, or a 3 dB frequency omega h can be also be determined from the plot of fh of s, fh of j omega, or the mod of that particular thing. Anyway, let's not try to worry much on this particular thumb rule. We'll try to figure out how do I determine the omega h when I try to discuss the open circuit time constant determination of the fh. There will make the every concept in determining how do I determining the omega h or fh can be made very clear when I talk of that particular concept. Now the one of the method that can be taken into account when I want to determine the omega h is, like I said, it's the function is the concept of transfer function. Now this is the transfer function I have. I straight away substitute s equal to j omega. Once I take the substitution, and if I take the squared magnitude, that will fetch me a value of this particular thing. By definition, I know that dominant pole terminology omega, or I'll be very interested in that particular pole which is very dominant, and I can also write omega wherever I have omega is equal to omega h, because I am interested in the higher cutoff frequency. Upon writing that particular replacing omega with omega h, and after doing simplification, this is the equation I am going to get. Upon further simplification, I am going to get the omega h value equal to this. Now this is what I am going to get, that is omega h, that is upper cutoff frequency, given by 1 upon under root of 1 by omega p1 square plus omega p2 square minus 2 by omega z1 square minus 2 by omega z2 square. Now I can extend the above this particular equation to any number of poles and zeros, and we can get this entire generalized expression. Remember, in all these cases, my region of interest will be this omega p1, that is a dominant pole, wherein I can say that the frequency where the pole exists will be the frequency of my, or will be the upper cutoff frequency of my amplifier configuration. Now let us try to understand this concept by a simple numerical. Now this is the numerical. The high frequency response of an amplifier is characterized by the transfer function given by this. Determine the 3 dB frequency approximately and exactly. Now we have a given transfer function being mentioned over here. Fh of s is equal to 1 minus s by 10 raised to 5 divided by 1 plus s by 10 raised to 4 multiplied by 1 plus s by 4 into 10 raised to 4. Now I need to be finding out the zeros and poles. Now I can find out that zeros, there is only one zero, that is at 10 raised to 5, and there are two poles. One is at 10 raised to 4 and another is at 4 into 10 raised to 4. Now we have learned that the general equation to determine the omega h. Let's try to use that. Omega h is equal to 1 over 1 plus omega p1 square plus omega p2 square, since there are only two poles, minus 2 by omega z1 square. Since there is only one pole, I will be mentioning z1. If there would have been two zeros, I would be mentioning again one more minus 2 by omega z2 square. And sorry, once I simplify by substituting the relevant values, I am going to get omega h equal to 0.98 into 10 raised to 4, or in terms of radians per second, it is 9800 radians per second. So this is your approximate value. Now this is how I can simply determine the high frequency response of an amplifier characterized by any transfer function. Now for exact value, I need to be I need to be substituting omega is equal to omega h, and f of h square is equal to 1 by 2. So 1 by 2 is equal to 1 plus omega h square by 10 raised to 5 whole square. I mean, basically I will be squaring out this entire term. So that will be 1 plus, since when I square this entire term, when I replace s equal to j omega, j square will be plus 1. So that makes this entire negative term to go as a positive. So that will be 1 plus omega square, and even I am replacing omega is equal to omega h, so that makes 1 plus omega h square divided by 10 raised to 5 square, that makes it as 10 raised to 10. Similarly for the poles over here, that will be omega h square divided by 10 raised to 8 divided by multiplied by 1 plus omega h square divided by 4 into 10 raised to 4 whole square, that makes 60 into 10 raised to 8. Once I simplify this, whatever the value I am going to get, that will be my exact value of the upper cutoff frequency, that is 9537 radians per second. So this is how I can figure out the upper cutoff frequency of an amplifier configuration using simple transfer function methodology. Down the line in the subsequent lecture, we are going to see how do I determine the upper cutoff frequency using the method of open time circuit constant method, which is very important in understanding the upper cutoff frequencies, and that is the most suited and apt method to find the omega h value. So to summarize, in the today's lecture, we had understood the concept of frequency response of MOS amplifiers specifically at high frequencies, and we figured out how one can obtain the omega h using the method of transfer function, and we also glanced to the different guidelines that are to be followed in order to determine the high frequency response of the amplifier, specifically when I deal with the transfer function methodology. So basically I need to be considering, or I need to be taking care of that dominant pole in the entire transfer function, and if I could be able to find the dominant pole, then definitely that the frequency of that particular dominant pole will be the frequency where my amplifier's highest frequency will fall in. Also, we saw in this today's lecture how much that omega h plays a vital role in order to find, or in order to justify any amplifier's performance. The performance of an amplifier is mainly represented by its gain and its upper cutoff frequency, the frequency up to which it can sustain the highest frequency, so that, or highest gain. So that frequency plays an important role whenever we talk of a high frequency response of an amplifier, or basically when we talk of the frequency response of an amplifier. Though the low frequency response we don't consider, because of course low frequency response does also have an impact on the working of the amplifier, but when we talk of a low frequency response, since it is operating at a very low frequencies, if I could find the omega L value considering the impact of certain capacitances, that will be much sufficient with respect to the amplifier configuration. But when I deal with respect to the high frequency or the upper cutoff frequency of any amplifier configuration, then considering the impact of all the parasitic capacitance becomes very mandatory, and I need to be thoroughly taking care of all those things whenever I determine any amplifier, amplifier's performance in terms of its frequency response. Hence, in today's lecture, we did all that exercise. And the probable semester end question that could be asked in the exam could be explain the general consideration for high frequency response of the MOS amplifiers. That could be a straightforward question. So in the very beginning of the lecture, we said that this is falling under the level 2, that is understanding the concept which we mentioned over here. We mentioned that this particular the entire exercise is all to understand how do I cater the need of the amplifier configuration in terms of its frequency response. So that is all for the today's lecture. Thank you for patience listening. Thank you.